So thanks. I'm talking to you from Nipaluna, Hobart, and not from Townsville today. But this talk focuses on theme 5, pesticides of the consensus statement, including herbicides, insecticides, and fungicides that you know all about. And I'll also touch on theme 6, which covers other pollutants. But before I start, I'd really like to acknowledge the efforts of all the authors, because we're talking about six different chapters here. And all their names are down in the bottom right-hand corner. I'd especially like to make a mention of Michael Warren. He sadly passed away not long after the final draft of Chapter 5.1 was completed. Now, Michael was he really committed much of his career to improving our understanding of the potential risks of pesticides in Queensland waters, and especially the Great Barrier Reef. He was a very generous friend and collaborator, and he played a critical role in writing that pesticide chapter, which was the largest chapter in that I'll be presenting today. So while I'm here, I'd also like to thank Jane and the team from C2O for the excellent coordination of not just this work, but all the work in the consensus statement. So the pesticide theme was grouped with the other pollutants theme, and it drew from a combined body of evidence of almost 700 peer-reviewed studies. I think you've probably already heard that all the sources need to be peer-reviewed. So theme 5 on pesticides was split into 3 chapters. So I led chapter 5.1, which assessed the spatial and temporal distribution of pesticides and their ecological impacts and risks. So as mentioned, I'm from the Australian Institute of Marine Science, and we generally had a high level of overall confidence in this chapter. There's always more we can learn, of course, but there was really quite a large number of new and relevant publications and a lot of published monitoring data, especially compared to many other chapters. So we were quite lucky, but there was a lot of material. Chapter 5.2 on the delivery and sources of pesticides. So this chapter was led by Shelley Templeton. So she's from Tropwater at James Cook University. And Shelley and the team had, they rated the confidence as medium to high for that particular chapter. Chapter 5.3, that reported on the effective management practices for reducing pesticide risks. So it was led by Aaron Davis, also from Tropwater at JCU, and the confidence was rated by Aaron and his team as medium. Much of the data was at a farm scale rather than at a greater scale, so that there was more to learn there, but I'll talk a little bit more about that later. And finally, Chapter 6, which reported on the spatial and temporal distribution of other pollutants, their risks and primary sources. This chapter was led by Anthony Charrington from Macquarie University, and unfortunately there was really quite a low confidence in the information that he was able to find for this chapter. There was not a lot of information on in terms of monitoring of other other non-pesticide pollutants, and also their potential toxicity. So this slide shows some of the headline findings from both chapters 5 and 6. So for pesticides, they're certainly ubiquitous across virtually all aquatic environments of the Great Barrier Reef catchments and in the nearshore marine environments, at least at certain times of the year. So they frequently occurred at concentrations that exceeded ecosystem protection guidelines in freshwater, particularly during those first flush events. And this is where a proportion of the pesticides applied leading up to the wet are mobilised from the land into the catchments by these early rainfall events, and they make their way down towards the coast. So exceedances did also occur in some marine sites, but they were much less frequent, and they were typically associated with flood plumes. So definitely the risk posed by pesticides in the Great Barrier Reef ecosystems reduced with the distance from the source as the concentrations decrease through dilution and other processes. So although the pesticides are commonly detected in marine waters, it's the ecosystems in the freshwater, especially higher up in the catchments, which are at greater risk. There's definitely a whole bunch of management practices that can reduce those risks of pesticides to GBR ecosystems, and we'll cover that a little bit later in the presentation. And Chapter 6, to finish off on the non-pesticide pollutants, revealed that there's really far too little known about the distribution, the concentrations and the potential impacts of these other pollutants such as metals, PFAS, coal dust, to really comprehensively assess the environmental risk to the Great Barrier Reef. But I'm not going to concentrate on that anymore today. We'll just talk mostly about pesticides. So this slide covers or starts on covering some of the main summary points from Chapter 5.1. I mentioned that pesticides are detected in the vast majority of all monitored freshwater, estuarine and marine ecosystems of the Great Barrier Reef. Importantly, they usually occur in mixtures. And so what's really been important since the last consensus statement is the development of the pesticide risk metric. So this has made it possible to estimate the total risk posed by the multiple pesticides that are detected in a mixture. And so there's now 22 pesticides in the pesticide risk metric, and that number is growing substantially. It's going up to more than 50 by the end of the year, hopefully. So the sites that face the greatest risk of pesticide exposure include those in the Mackay-Whitsunday region, like Sandy Creek, and also to a lesser extent, some sites in the Burdekin, such as Barada Creek. I'll talk about Barada Creek in a moment, but those sites consistently record higher concentrations of pesticides than most other locations, and similar findings were reported in other consensus statements. These are really consistent findings. So this slide shows the end of the catchment overall wet season risk, and it's calculated from the pesticide risk metric. So this is how we pulled some of the data together. And so this is end of catchment. And so I've highlighted the Burdekin sites in that big red box there. We've got Barada Creek, the Horton River and the Burdekin River. These essentially represent different types of systems. You know, Barada's small, doesn't have a lot of flow. The Burdekin, on the other hand, is enormous and has high flow. And so if we look at this small red box here, this number 94.7, this indicates that about 95% of species are predicted not to be at risk of pesticide mixtures over the 2019-20 season at the Horton River, or in other words, about 5% would be expected to be at risk. So essentially, the higher the number, the less risk. And so if we look at the green cells across here, they indicate there's very low risk in the Burdekin over those wet seasons. Conversely, at Barada Creek, you've got the orange and the pink cells up there indicating much higher risk. So essentially, what we really found was that the lower rainfall in the Burdekin dry tropics compared to, say, similar sites in the wet tropics means there's often less discharge from the rivers and creeks in parts of the Burdekin, and less dilution of the pesticides at some sites, especially like at Barada Creek. Now, this is a really common pattern across the catchments, but it also means that some sites with really, much higher pesticide loads, they can present lower risk if there's a lot of rainfall or a lot of discharge to dilute those pesticides. So that might be the case in the Burdekin River, for instance, where you've got large flows during the wet season. So most of the risk, according to the pesticide risk metric in the Burdekin, was really due to diuron, atrazine and imidacloprid, and that's pretty typical of a lot of other sites as well. Interestingly, there was an alternative herbicide which started turning up, so isoxaflutol at Barada Creek from around 2020, and that contributed a smallish but a significant proportion of the risk of 17 to 13% over those later years. So we had a range of similar conclusions for the other regions. We didn't have enough resources to report on every single site, so we chose 12 sites, which were somewhat representative of different catchments within each region. And we did the same risk assessment for the marine monitoring sites as well. So the temporal trends, now there has been a lot of monitoring data available, but there haven't been very many publications on the really long-term trends in pesticide risk over time. However, there was one publication that we came across which did a long-term analysis, and that indicated that photosystem 2 herbicide concentrations remain fairly stable at most marine sites, but at some inshore marine sites, they increased between 2005 and 2018. So they were actually going the wrong way compared to what we'd hope. However, well, these sites included Low Isles, Serena Inlet, and North Keppel, but the risk there still remained pretty low. But that's certainly something to look out for. It's a little bit unexpected. There was also a report which looked at some reasonably long-term trends of imidacloprid, and it found increasing trends at several sites, including at Barratta Creek. So I've got the graph of Barratta Creek up here, and especially from about 2014 to 2016. But you can see that it rapidly decreased after that. Apparently, it was brought to the attention of industry, and it seems like it's a great example of adapting management to reduce the risk or the perceived risk. So the consensus statement highlighted a recent study from CSIRO, which coupled the end of catchment loads for just diuron, with a three-dimensional hydrodynamic model in e-reefs. And this simulated diuron concentrations in nearshore waters, marine waters, from 2016 to 2018 in hourly increments. It's much more sophisticated than anything that had been done before with pesticides in the Great Barrier Reef. So I got a couple of images up from that publication, which we did report on in the consensus statement, and you can see that the Burdekin region here, and we've got some darker shaded areas there which indicate higher predicted diuron concentrations. Now, if we just look at that marine monitoring site over time and the diuron concentration there, and here you can see that there's very low concentrations for quite a lot of the year. When some of these very early rains came in, you can see that diuron was predicted to be washed from, they're calculating this from the loads at the river mouths, but they're predicting that at that site, the diuron concentration, peaked for about a month over this period here. And so you can see it's up around about 0.4 micrograms per litre, and you can see the relevant guideline value there for 99% protection. But certainly these models are definitely very promising. I think they're developing more models now, but they really need to include other pesticides, because we could see diuron was making up about, maybe 30% of the risk at that Barratta site. And of course, we need to do further validation of those models. The validation in the publication was pretty good. It wasn't always spot on. We certainly need more of these types of models so that we can really predict what happens over time. And you can see how spiky it is as well, which is pretty interesting.
Andrew, I'm sorry to interrupt you. You've got about 5 minutes left, just so we have some time for people to ask you questions.
Oh, right. Okay. Yep. Sure. Okay. I'll have to rush through it a bit then. So there have been a number of recent experimental studies which have tested the toxicity of pesticides on Great Barrier Reef species as well. That's actually been my particular area of interest. So pesticides were found to be harmful for many of these non-target GBR species, including seagrass, for example. But the risk really depends on whether the concentrations in the environment exceed the toxicity thresholds. And of course, that isn't always the case, especially in marine systems. Importantly, for the risk assessments, we found the toxicity values in the pesticide risk metric were protective of GBR species, both the freshwater species and the marine species. So that was really comforting. Finally, from this side of it, there's also mounting evidence that pesticides can increase the vulnerability of some GBR species to other stresses such as heat waves. So I wasn't aware I'd be presenting chapters 5.2 and 5.3 until lunchtime, so I don't know this part as well, but I'm going to go through the slides. Chapter 5.2 was led by Shelley Templeton on pesticide sources and drivers, and they found that sugarcane remains the main source of pesticides, but there's an increasing awareness of other contributing agricultural and urban sources, but it's really the scale of the application on sugarcane that makes it the main source in the region. The timing and the rate of application has a massive influence on pesticide export. This includes the rainfall, the irrigation regimes, the pesticide and the soil properties. And critically, the time between application and the rainfall is really the largest driver of pesticide export from sugarcane. And they also found that most of the pesticide runoff occurs in the first 25 days after application. So it makes sense then that the longer the time frame from application to the runoff event, then the lower amount of pesticide exported. Certainly the first rainfall event of the wet season that I described earlier as the first flush often delivers the greatest proportion of pesticides to the Great Barrier Reef, and we saw that spike in the graph I showed you a minute ago. In irrigated areas, the greatest loss of pesticide also tends to be associated with the first irrigation event, so it's similar for irrigation as well. Now, pesticide contributions typically reduce with subsequent rainfall events, so while pesticide export profiles from irrigated sugarcane are similar to rainfall events, irrigation can lead to higher ecological risk in receiving systems, and this is often due to longer exposure periods and less flushing and probably less dilution as well. So from chapter 5.3, Aaron's team found that the most effective management practices to reduce pesticide risk from agricultural land include reducing the total amount of pesticides applied. It's pretty obvious. Optimizing application methods. So this could include, for instance, more targeted methods such as spot spraying. Optimizing the timing of the application to when there are periods where there's less rainfall or less chance of rainfall. We can never be sure. Choosing pesticides with lower environmental risks. So this can take the form of products with lower environmental toxicity or less environmental persistence or great absorption to organic matter in the soil, for instance, to reduce mobility. And there is a new pesticide decision support tool that can help with that. Reducing soil erosion and improving the irrigation efficiencies are also important. Pesticide resistance is likely to require changes in the pesticide use and the uptake of other alternative pesticide or pest control measures into the future. So a range of non-chemical pesticide control measures such as integrated pest management and cultural controls that modify the pest's growing environment apparently hold great potential for reducing the reliance on chemical control measures. The main problem, though, is that really most of these alternative approaches have not been trialled really to gauge their success with respect to long-term pesticide use reductions and efficacy and economic outcomes. So more work needs to be there. They report that more data is required to assess the management effectiveness of many emerging insecticides and fungicides as well, used in the Great Barrier Reef farming systems. So I think this is the last slide, but Aaron's team found that there remains a lack of frameworks, risk-based metrics and inconsistent assessment methods for cost effectiveness. And this really posed a challenge for their team to assess pesticide management practice change. Economic returns remain critically dependent on region-specific variables, including the biophysical characteristics, enterprise structure, especially in relation to the farm size and location. And for sugarcane, progressing from traditional to industry standard herbicide management was reported to be generally profitable and provide return on investment across basically all farm sizes and sugarcane districts, which is a good story. So hopefully I've finished in time. That pretty much winds up what I've got. Thank you.